we just had a look at how to select an algorithm and then also how to train it. So next up will be the model performance evaluation. So assuming now that we've already trained a machine learning model, it's finally time to start talking about how we can actually evaluate the performance. So this will be the numbers that we need to report back to our stakeholders, how well the model is doing. Before we can actually get those numbers, there is one important thing that we need to do, and that is the train, test and validation split. Generally, when we build a machine learning model, we would take our original dataset and split it into the so-called training and test proportion. The training set is what we use to actually train the model, so that will be learning the parameters or the different settings. Think back to the different hyperparameter choices that we have. And then we report back the performance on the test set, which is basically emulating a production environment. So this is the data that the model has never seen before. We do have an additional split in the training set between train and validation, and that is exactly for the purpose of finding the best possible combinations of hyperparameters and tuning the model, or even trying out different models altogether. So the top half is going to be a very iterative process between the training of the model and validating its performance. And eventually, once we're happy with the performance, well, then we get a final evaluation on the test set. And then we'd be reporting all those numbers back. So what is the performance of the model on training, validation, and also test? If we want to create these splits, there are a few points that we need to consider. First one being that we need to shuffle the dataset before the split. Generally, when data is collected, it's done so in a certain order. Thinking back to our example of different populations or branches of banks, you might want to start collecting data in the US East Coast and eventually you move on to the West Coast, meaning that the majority of the data that you have in the top half of your data set would be coming from East Coast, and then eventually you would come down to West Coast population. So if you just split the data top to bottom, well, then you would have an overrepresentation of a certain population in that data set. How are these splitting ratios? What do they look like? Well, generally anything between 80-20, 90-10. You want to keep the majority of the data for training and then a small proportion for the test and validation. What we also need to make sure is that we have identically distributed data in all these different splits. So we want to make sure that the different subpopulations are represented equally in the different splits. There's one technical challenge or caveat to this, and that is sklearn, which has an implementation for the train test split, does not actually allow you to directly implement or use protected attributes. So you need to come up with your own stratification of the different subpopulations. If you want to learn more about train test and validation split, there is a great article on MLU Explain about this. It's an interactive visualization and it shows you how exactly these splits work and what to consider. Coming back to our model evaluation now. We want to make sure that models are fair and also perform well. So we have two different objectives. On one hand, we want to maximize the performance of the model, and on the other hand, we want to uphold the fairness of the model. And any model that does not meet the above criteria, so if the model is not fair or does not perform well, well, then we should discard the model altogether and start from scratch. Let's start by talking about the performance of the model. So here we have an example of a regression. And to evaluate the performance of a regression model, we need to look at the individual data points, the true points, and compare them to the prediction line. How can we compare them? Well, one measure would be the distance between the true labels, or the true scores, and the prediction line. So step number one is going to be find the distance, and here we could take the square distance or absolute distance between the prediction line and the labels or scores that we have. Step number two is going to be aggregating everything up to one value. So it's not very practical to have all these individual scores, all these distances recorded in a long list. We want to aggregate everything into one value. How can we do that? Well, we can add them up, but then we want to divide by the total number of data points. One popular equation here that's being used as a measure would be the so-called mean squared error. So you can see here it's 1 over n, 1 over the number of data points, times, and here you have the sum of yi minus yi hat. The yi hat are going to be the predictions, and the square to square the distance, and penalize data points that are further away from the line more. What you might also notice here is that we're not talking about group membership yet. So nowhere in this equation, nowhere in MSE would you find a reference to different subpopulations. Moving on to an example for classification. So in the case of classification, we cannot calculate the distances. Keep in mind that classification is going to produce outcomes like blue or red as different classes, or ones and zeros, and you cannot directly subtract those values. So I want you to keep the blue-red example in mind for this. You cannot subtract two colors to get a meaningful value. So what we can do instead is we can list how many times the prediction, the predicted label that we created, agrees with the ground truth. And if we do that, and it's a binary classification example, then we can have a confusion matrix as is shown on the left-hand side. So here you can see on the top we have prediction 1 and 0, so positive and negative. And on the left-hand side axis you have the true state, again positive or negative. And then we just count how many times did we get it right. So how many times did we predict 1 and the true outcome was actually also 1? How many times did we predict 0 when the true outcome was 0? And how many times did we get it wrong? So these are the values of the diagonal. We could be predicting 0 when the true outcome was 1. So that would be a false negative. Or we could be predicting 1 when the true outcome was negative. And then it's a false positive. So once again, this is going to be too many different numbers. We want to sum it up in one value. So how can we sum this up? Well, what we could do is we could count how many times we got it right, so the values on the diagonal, and once again divide by the total number of data points that were used. So that then gives us the so-called accuracy value. A few points to consider now. So in regression example, MSE, and the classification example with accuracy metric, we did not see any particular mention or reference to group membership. So really what we need to do is we need to extend this further and talk about how we can actually evaluate the performance of a model on different groups and ensure that it's really fair to different subpopulations. The other point was that it's very important to have this train, test and validation split, because it could be the case that the model would simply memorize the training data and then not generalize well. So really you always need to calculate these metrics, whether it's MSE in the regression case, or there are many more, or accuracy in the classification case. You always need to make sure that you have the train, test and validation split. As we just saw, common evaluation methods don't consider different group memberships. So really what we need are fairness-specific model performance measures that specifically call out different groups. One very simple example would be taking an existing measure, such as accuracy, which was the performance evaluation for a classification model, and simply calculating it per group. So here now we have the same data points as earlier, but we're overlaying with different group membership, group A and group B. And what we can immediately notice is that the performance, the accuracy on these different subpopulations is vastly different. On group A, we have an accuracy of 0.81, group B only 0.4. Keep in mind that for accuracy, the closer to 1, the better, because it means that we got everything right. So here, how could we compare the performance in the different groups? Well, we could take the difference between group A and group B. And the closer to 0 now, keep in mind this is the difference between accuracies. So the closer to 0 the difference, the more similar the performance is for the different subpopulations, and the better the performance in terms of fairness. So really we need to calculate two measures here. We need to calculate the overall machine learning performance, but then we also need to make sure that we calculate it per group. So what would we do if we had more than two groups? Well, we could look at the max absolute difference, so we could calculate the differences between all the groups and find out which groups have the biggest difference, for example. Once again, this is only one example of a measure. That would be the simplest approach. Take the existing evaluation that you want to perform and split it per group, and then check if the measure is still looking okay. Now we're going to have a look at the calculation and also training a model from scratch here using the logistic regression notebook. And in this notebook, we're going to build a logistic regression, and then we're going to evaluate the performance using accuracy difference and DPPL, which is the difference in positive proportions in predicted labels now, and an extension of what we've already seen earlier as DPL.